Okay, let me um, so conservation of mass number 3. Um, it's refrigerant 134A. That's something that we have tables for. It enters the condenser refrigeration system with a steady state. Uh, so at the inlet, so we have an inlet, exit. At the inlet, the pressure PI is 9 bar. Um, and the area is 2.5 centimeters. I guess that's a diameter. Um, at the exit, the pressure is still 9 bar. Um, the temperature at the exit is 30 degrees Celsius. And the velocity is 2.5 meters per second. Um, the mass flow rate entering, so M at the inlet dot is 6 kilograms per minute. We're going to want to convert that and do this whole thing in SI units. And we want to calculate the velocity at the inlet, the diameter of the exit pipe, and okay, so it's a condenser. So what do we know about a condenser? So a condenser is used to turn a vapor or a saturated material into a liquid, or to make more of it a liquid. Um, it's steady state. So so steady state means that um, dm dt in the control volume is 0, and so the mass rate flow at the inlet is equal to the mass rate flow at the exit is equal to m dot. We're given what that is, right? Yeah, so and that's equal to 6 kilograms per minute is so divide by 60 and you get 0.1 kilograms per second. Um, and so we know that ME dot is 0.1 kilograms per second. And we know that that's equal to the area at the exit times the speed at the exit divided by the specific volume at the exit. Um, we're given the speed. So we have A exit times 2.5 divided by specific volume at the exit. And what do we know? We know the temperature is 30 degrees Celsius and the pressure is 9 bar. So we know two properties. That's enough to look up any other property that's in the table. And so the property that we would like to look up is the specific volume. And so, look up 30 degrees Celsius and 9 bar in, it doesn't say anything about what the state of this material is. So we're going to have to look this up in 3 different spots. The fact that it gives a temperature and a pressure often suggests that it's not saturated, because it would only have to give us one of those if it was saturated. But which makes me think it's going to be in the water liquid table. So in the water liquid table, so what we're really looking up is V at those two. And so that was a long way of answering what you asked about. Yeah. So, but if you look this up in the liquid table, you get V is equal to 1 over rho. And the answer, I guess, is 1 divided by 1199.7. I guess I looked it up and then converted it into a density. There's not really any reason you have to do it that way, but whatever this number is, that's just what I looked up in the table. Yep. Oh, yeah, not water. Yeah, refrigerant. And then, that makes me think, I don't know if I gave you a, for liquid, because I know there's one for saturation and one for vapor. Whenever that happens, that I give you a material that you don't have the table for, that's a mistake that I made, that, it's in this long list of things that are going to be ironed out over the next couple of times I teach this class or whatever. So sorry about that. But you can almost always just Google refrigerant 134A liquid property table or something, and it'll come up from a million different sources, and you can find it that way. Yeah. Okay, yeah. Yeah, right. Yes, you're not crazy. So I'm pretty sure there's no liquid table that I gave you for that. It's easy to Google. And then once you have that, you can solve for the area, and then if you assume, well, it says diameter, so that means it's round, and so you can just use the area calculation for that. Any other homework questions?
I did it incompressible and ideal number 3 a couple different ways. And you did mention that you're calculating some different results.
Right.
So the final step was to calculate the standard error. And one of mine was like 28, one of mine was like 18. So
that's a pretty big difference.
Yeah, it's pretty large.
What are the, can I see the question?
Sure. That's going to be part A of number 3 there.
Okay, so in using the ideal gas model to determine the specific volume of, and for A, um, so we want to calculate the specific volume for water vapor at a pressure of 10 kilopascals, pretty low pressure, and 100 degrees Celsius. So we need to know for water the molar mass. So this constant R is equal to the universal value of R divided by the molar mass. And M is equal to, what do you get for water? 2.02 plus 16, is that right? 16.00, so 18.02 about. And in SI units, that's kilograms. No, that's times 10 to the minus third kilograms per mole. And so R is equal to 8.314 divided by 18.02 times 10 to the minus third. And what do you get for that number? 461.38. Okay, and then, so we have a pressure of 10 kilopascals. So 10 times 10 to the third pascals times the specific volume is equal to 461.38 times the temperature, 100 Celsius, which is 273.15 plus 100, so 373. I'll just leave it like that. And so can you calculate V? $17.22 meters cubed per kilogram. And so now we need to look it up in the table and see how close this is to. So we're talking about water vapor. Anybody have that? Do you have that table with you? Okay, so yeah, just give me some values. Okay, let me, so this is 80 and what's the pressure?
Yeah, I'm sorry.
Yeah, so you have temperature and pressures. So you said 60 or 80, sorry. Okay. Okay, 80 degrees Celsius and what was, and that's in megapascals or something? Okay, so 0.0, 0.06, 006 MPa. Okay, and what do you get for that? Okay, and that's, okay. Mhm. 120. Okay. Okay. And then 80 Celsius, and what's the other pressure? 0.035. Okay. That's the specific volume. 4.625. Oh yeah, it's vapor. It's vapor. So okay, 4.625. Okay, so if I have a bad habit of like I see water and I think liquid, but a liquid changing the pressure doesn't have much of an effect on the specific volume. Um, a vapor, you know, you can smush a vapor pretty easily, so that specific volume can change a lot. And then the last one is 120, and then 0.035, and what's that one? 5.163. Okay, and so you said, okay, so we're doing an interpolation over a huge range of values. Yeah. This one down at the bottom, that's 23.739. Or did you just look it up? Oh, 27.132. Okay. 27.132. Okay, well, that could make a difference. I was going to say, this is a pretty big percentage difference. And so it's like interpolating anything, a linear interpolation of anything that's not linear, the bigger the range is, the more error you can have. But now I'm sort of curious if just with that new value, it comes out different. Yep. Yeah, we would say the table. So the tables are made from much less simplified equations. They're still calculated. It's not like you can measure this stuff, but they're using more complicated equations. And so you should think of the table values as the true values. And our ideal gas model is what we're testing, kind of. Well, yeah. Hmm. Hmm. Yeah. Let's do this. Let's do it. Okay, so first, let's say, so the specific volume at, let's say, what are we trying to go to? 100 Celsius. So at 100 and 0.006, um, is 27.132 plus quantity 30.219 minus 27.132 divided by 120 minus 80 times 20. Can someone punch that in? Okay, and then the specific volume at 100 and 0.035 is 4.625 plus quantity 5.163 minus 4.625 divided by 120 minus 80, and then times 20. And what do you get for that? 4.894. And then the specific volume at 100, and we're looking for 0.01. is 28.67 plus the quantity 4.894 minus 28.67 divided by point oh one, nope. Okay, divided by 0.035 minus 0.006 times 0.01 minus 0.006. And what do you get for that? 25.39. Okay, so that's our first value, and that's in meters cubed per kilogram. Yep. Mhm. That should give you the exact same values, actually, as long as you, well, as long as you keep everything in the same order. Like, so we could call, so like, I'm calling this my x1 and this my x2, and this is my y1 and this is my y2. But if you call this your y2 and this your y1, it'll still give you the same exact answers, not close, the same exact answers because it's the same line, as long as you switch the order of everything corresponding. Otherwise, like if you flip flop, like if here instead of doing this, you do 28.67 divided by 4.894, but you don't flip the order of these, then it'll send you going the wrong way along that line. Okay, so that didn't take too long. Let's do the other one and see how close they are. Just do it in the other order. So, uh, so here was our final value. So now let's go specific volume at 80.01. So at 80.01, so we're going to go 27.132 plus the quantity, where is it? 4.625 minus 27.132 divided by 0.035 minus 0.006 times 0.01 minus 0.006. And what do you get for that? Oh, I thought you were just calculating those that fast. You just had that in your paper. Sort of disappointing. That makes me feel like all of a sudden this is going to take a lot longer than I thought. .027. Okay, and then specific volume at 120 and 0.01. So 30.219 plus the quantity 5.163 minus 30.219 divided by 0.035 minus 0.006 times 0.01 minus 0.006. And can you calculate that? 26.763 meters cubed per kilogram. And then the final answer, specific volume at 100 degrees Celsius, 0.01 is 24.027 plus the quantity 26.763 minus 24.027 divided by 120 minus 80 times 100 minus 80. And what do you get for that? Wow. That seems suspiciously, enticingly close to being exact, doesn't it? Anyways, so we get these two answers that at a minimum are very, very close. And then we're comparing that to an answer of, so 17 compared to, okay, so we have 25.39 minus 17.22 divided by 25.39. 2%, which isn't that great, but I mean, as an approximation. I've seen worse approximations than that. So by the way, 100. So you would expect, so this is water vapor that is just above the saturation temperature, right at the saturation temperature. This is like basically saturated water gas, okay? Would you expect this approximation to get better if the temperature increased or worse? Better, so that the ideal gas approximation is best for low pressures and high temperatures, okay? So if you're at the lowest temperature you can be at, that it can even have the identity of being a vapor at a given pressure, then you're getting pretty bad results. Okay, so part B asks you to do it at a much higher temperature, and I assume that you get a lot closer results for that. Any other homework questions? Yes. Okay. You have it with you? Oh, this is the one, okay. This is one where the table doesn't go high enough, I think, if I remember right. Or low enough or whatever. And so we did this one in office hours today, and we just had to Google it, and we found it online. So number 4, this is First law for control volumes, part 2, 1. So we know we're going to start with this equation. So I'm going to start with this, and then we'll think about what we can eliminate. It's refrigerant 134A. It's an insulated diffuser, and insulated means that this goes away. It operates at steady state, so there's no DEDT, and there's only one mass flow rate. It's the same at the inlet and the exit. Ignore potential energy effects. And then we know that at the, let's see, and it's the diffuser, so it's solid. So there's not going to be any work done by expansion or contraction. At the inlet, there is a speed of 1,200 feet per second. Do you have those all in SI units? You have those with you, Max? So what's the speed? Yeah. Okay, that's meters per second. And then the pressure, if you convert that to SI units, 6.895 bar. And then we know that the speed is negligible at the exit. The pressure at the exit, what was that when you converted it? Our simplified equation, now that we've eliminated everything that we can, says, well, you can divide everything by m dot, and you just end up with an equation that says, you can write it as H inlet minus H exit is equal to 1/2 times V exit squared minus V inlet squared. Yep. We're ignoring that. It says that's negligible. And so we know this. It starts as a saturated vapor. So at the inlet, it's a saturated vapor, which means having the pressure is enough to look this up in a table. So the enthalpy at the inlet comes from the saturated table. And so this is enough for us to calculate the specific enthalpy at the exit. And now that we know, so we know the pressure at the exit, and the specific enthalpy at the exit. And that's enough to do, to look up the, what are we looking for, the temperature? So we can look up the temperature in the table. The one that you have will not work. So you need to Google a table. You can use another browser or whatever, if you want. You don't have to use Google. You don't have to use Google brand search engine. But you need to find one that has this. So this specific enthalpy and this pressure. We found one. Question? Okay. Any questions about this? Any other homework questions? Okay. Okay, so we have exam 4 a week from today. And so what I'm going to do before I get into the next topic, which is a pretty big departure from what we've been doing so far. So I just want to go through sort of a careful outline of all the things we've done up till now in the class. And I guess I probably won't finish it today, but I'll finish it, in the first half of class tomorrow or whatever. So exam 4 is Tuesday. I guess that would be the 13th. And the topics will be everything up through this. So we're not going to have any of the new stuff involving entropy on it. And the second law of thermodynamics, that won't be on it. So up through the first law for control volumes. And remember, it's cumulative, so all the stuff before will be on it too. So here's an outline of everything before the second law of thermodynamics. So first was just the introductory stuff, some talking about energy and pressure. And so the first thing I talked about was pressure. And the equation that we dealt with in this section was P, I don't remember how I numbered these. Let's say just P is equal to P1 plus rho GH. Where this was the pressure at the deeper spot, and this was the pressure at the shallower spot, less depth. And we talked about barometers and manometers. Thank you. Um, and then after pressure, we talked about work. What? What about it? This is going to be positive, and the pressure is always going to be higher the deeper you go. So yeah, that's right. Do I have it backwards in my notes somewhere? Okay. Well, sorry about that. If you bring like a deep water tank, you could remind yourself, like if you can't remember, just like put your head in deeper and shallower and feel where the pressure increases. I don't know. That might not be practical. Um, and work. So there's really only one sub thing that I think is uh, worth putting on here, and that is that the work done by expansion or contraction is the integral of P dV. And remember that that volume is the total volume. That's not the specific volume that we're more used to dealing with. And that goes from state 1 to state 2. And then I'm not going to put down equations or anything, but remember that work also includes things like um, rotating shafts that are being powered by the system or that are putting work into the system, or electrical power. So those are really the main things that you have to include as the work. And then we got to the first law of thermodynamics. And that's for closed systems. And so that means that our system is a collection of matter, and it's going to, through the whole time we're analyzing it, we're going to be focusing on that same matter. And so first we talked about it in this form. The change in energy is equal to Q minus W. And this is where we introduced the really major sign convention issue of this class. So this is the heat that goes into the system. And this is the work done by the system. Even that isn't really super careful language. Like more careful language would be a positive value of Q is adding energy to the system through work, through heat. And a positive value of W is removing energy from the system by work. And this is the change in energy in the system. Okay, there's sort of two subcases here. The first one is for steady state. And if something's in steady state, then there's no change in the energy. And then related to that, if you're talking about some integer number of cycles, so this thing doesn't have to be steady all the time, but if the amount of time that you're investigating this over as a cycle, meaning that it starts and ends in the same state, then you also have this, that the change in E is equal to 0. And then second, we talked about this in the differential form. So dE dt is equal to Q dot minus W dot. And this one, there's no such thing as a cycle if you're dealing with a single instant, like this equation does. So we only have this steady state. But if you're in steady state, then the rate of change with respect to time of the energy is 0. There's no change in the system's energy over time. And then after that, we talked about heat transfer. And heat transfer is really just using these three equations, knowing what to plug in where. It's not a very complicated idea on its own. The main complicating factor is just being sure that you deal with the sign convention. So remember, the equations don't follow the sign convention. That you have to use in the first law. After you use those equations, you have to think about, is energy being transferred through heat into the system or out of the system? And based on that, you give it a sign. So the first one of these equations is the conduction equation. That's called Fourier's law. And it has the form Q dot is equal to negative kappa times A times dt dx. This kappa is the coefficient of thermal conduction. And that negative sign really, for us, is not that useful, considering that we're not using this along with other equations to solve a big system of equations. It's easy for us to know which way heat is transferred. It's always transferred to the lower temperature. Okay, energy always goes from the higher temperature to the lower temperature. But all that negative sign says is that the direction of heat flow is the opposite direction of the temperature gradient. So you can just forget about that negative and apply the sign yourself based on where the lower temperature is. And then radiation. This is the Stefan-Boltzmann equation. And we have this in two forms. The first one is that Q dot that's emitted by a body is equal to epsilon times sigma times A times the temperature of the body to the fourth power, where this epsilon is called the emissivity. The sigma is the Stefan-Boltzmann constant. And the A is the surface area of the body. This E down here means that this is the amount of energy that's emitted by the body through heat. And so then once you choose your system, you determine the sign convention. This form is always true. You can always use it, but it isn't too useful for in the first law of thermodynamics. The one that's useful is like we don't really care how much energy something's emitting if we don't know how much energy it's getting back. So the one that's useful is the one that we can only use in some cases, and that's that Q dot that's emitted is equal to the emissivity times sigma times A times the quantity temperature of the body to the fourth minus the temperature of the surroundings to the fourth. So this one is the total heat emitted, total net heat emitted. That's sort of redundant. I'm going to just call it net. And that one's useful in the first law of thermodynamics. The problem is it only applies when you have a smaller body surrounded by a bigger body. Okay, so those are the three modes of heat transfer. Yeah, I didn't do that yet. Thank you. So convection, I don't have a name for that equation. In a way, it's not really like it's more of a sort of curve fit equation than anything else. You sort of lump everything into the one constant. So the rate of heat emitted through convection is equal to the constant H times the surface area that's exposed to the flow of fluid times the difference in the temperature of the body and the temperature of the fluid. And this one is just sort of a catch-all constant. Oh, temperature. Okay. And then the third big overall topic is material property relationships. Um, and we didn't spend a lot of time on this, but I first introduced the PVT surface. And you can look at the PVT surface in a bunch of different projections. And the three different projections that people use are the first one called the phase diagram. And the phase diagram is a pressure, it's in the pressure temperature plane. And then there's a PV diagram. And then a temperature volume TV diagram. And these should all be specific volumes. And then we talked about quality. And that quality only is a thing for a saturated material. And the definition of quality is the mass that's made up of vapor divided by the total mass, which is the mass made up of vapor plus the mass made up of liquid. And you can use this to calculate the specific volume, the specific internal energy, specific enthalpy, specific entropy, which we haven't talked about yet, for a saturated material. So for example, I'll do it for a specific volume. The specific volume is the quantity 1 minus x, 1 minus the quality, times the specific volume for the liquid, so that's V sub F, plus x times the specific volume of the vapor, so that's V sub G. And that same equation works for the specific internal energy, all of those. And next, I introduced enthalpy. Enthalpy is equal to the internal energy plus the pressure times the total volume as units of energy. And the specific enthalpy is the total enthalpy over M, and that's also equal to the specific internal energy plus the pressure times the specific volume. And then I introduce specific heats. And there are two of those. C sub V is, anyone remember what that is without looking at your notes? Partial of U with respect to temperature, holding the volume constant. And then C sub P is the partial of H with respect to temperature, holding the pressure constant. We didn't do this, but you can find like sort of power series formulas that give you the constants of all the different terms of the power series for some certain distance out along that represent these under certain cases in terms of like say temperature or whatever whatever's relevant for the approximation you're making. And then you can actually calculate these derivatives based on that power series. We didn't do anything like that. Yeah. Of those, well, I guess it would be joules per Kelvin. Yep. No, I'm sorry, because that's a specific internal energy, so it would be joules per kilogram Kelvin. And then we got to the simplified material models. And there are only two of those. The first one is incompressible. This is never really relevant for gases, but you use it for liquids and solids. Liquids are more important to us. And in the incompressible model, we assume that the specific volume is a constant. And what constant do you use? The best thing to do is to look that up at a temperature that's relevant for your analysis. So look it up for your temperature in the saturation table. And then we also assume that U is really just a function of temperature, that pressure doesn't change it very much. And because of this second assumption, we'll introduce this new C that's called the specific heat for an incompressible model. And we're going to treat that as being the same as C sub P, which is the same as C sub V, and that's equal to dUd temperature. And then next is ideal gases. We mainly use this equation. I think this is the only one I've used in solutions. P times specific volume is equal to capital R times temperature. Equivalently, you can use this one that says pressure times the molar specific volume is equal to R bar times temperature. R bar is the universal gas constant, so that's the appeal of that one. R is specific, whatever material you're looking at, and it's equal to R bar over the molar mass. That is the volume per mole. And it's just another, there's a one-to-one correspondence between the specific volume by mole and the specific volume by mass. So those are kind of equivalent, but you have to do a conversion to go from one to the other one. Anytime you see a specific property with a bar over it, that's talking about per mole. Mm-hmm. Uh-huh. Yeah, that's the same as that because this is volume per mole. So multiply the moles over here, and you get P times real volume is equal to number of moles times RT. But yeah, that's sort of the chemistry version. And really, the only reason that we use the other version is because the tables we use have all of our specific properties. You know, they could just as easily write out those tables in a molar form, and then we would use the one that you're more used to. And the big assumption that we make with an ideal gas, besides the ideal gas law, is that the internal energy is treated as a function of temperature. And therefore, C, let's see. So CV is equal to du dt. And CP is equal to CV plus R, right? Yeah. Okay. And let's stop there for today, and it'll take maybe 15 or 20 minutes to do the rest of this, and we'll do that on Thursday.